Morning, everyone. It's my great pleasure to be introducing Jan Volec. Okay, thank you very much. On the second day, welcome back to everyone. Jan is going to be talking about common graphs with large chromatic number. Please go ahead, Jan.
Okay, thank you very much for the introduction. Also, I would like to thank the organizers for inviting me and giving me the opportunity to speak here. So all I'm going to talk about today is a joint work with Kral, who's just here, and also he's from Masaryk University in Czech Republic, and with Fanway, who is in Princeton. So, okay, before I move on to the problem that will bother me and perhaps bother you for the next 45 minutes, let me start with some combinatorial motivation for these type of problems. And to go really back to the beginning, a classical result is Ramsey theory is that R3 equals 6. What does it mean? It means that if you take any red-blue coloring of the complete graph on 6 vertices, you have no way to avoid seeing a monochromatic triangle. So, okay, and if you give me a clique that is larger than 6 and you red-blue color it, well, I can forget n minus 6 vertices of it and still find one monochromatic triangle. But, and okay, so far, I guess I've said only one inequality of this R3 equals 6. Also, there is a 5-vertex graph. There is a coloring of a 5-vertex complete graph that has no monochromatic triangle. So this 6 is in a way best possible. But if you give me a large complete graph, perhaps we now know that you see at least one monochromatic triangle. As a matter of fact, already on those 6, if you red-blue color a K6, you see at least 2 monochromatic triangles, not only one. But if the graph you are coloring is large, it sounds natural to find many more copies, many more monochromatic triangles, not just 1 or 2. And indeed, that's true, because like one way of observing it is that if you look at any window of size 6, by Ramsey theorem, you see at least 1, well, now we know at least 2 monochromatic triangles. And if you move this window all over the place, just by averaging argument, you see roughly at least n cube over 20 monochromatic triangles. So one remark I want to make right away is that when I'm counting subgraphs, I'm counting labeled copies. So to some extent, every monochromatic triangle gives me +6 to my count, because there is 6 ways how to label its vertices. For triangles, it's perhaps rather an odd way of counting. It would perhaps sound more natural if I just don't introduce this artificial factor of 6. Soon we will be counting monochromatic copies of graphs that are much less symmetric. So in this labeled way, it will perhaps make my life easier to not care that much of the of the size and structure of the automorphism group. So I will be counting labeled copies during the whole talk. So, but even this argument that just moves this window and applies Ramsey's theorem in each of these windows sounds like a little bit wasteful, and it doesn't seem like this is the best way how to count. And indeed, that's true. And for counting monochromatic triangles, there is a result. There is an old result from late 50s of Goodman, which says that actually in any red-blue coloring of Kn, you see roughly at least n cube over 4 monochromatic triangles. And this result, so and it's known that this is best possible. I believe that this formula is actually best possible for every n. So, okay, so what about other graphs H than just triangle? And the game we would like to play is, again, that we consider arbitrary red-blue coloring of the edges of Kn. So Ramsey's theorem is not something special for triangle. It applies to every H. So for every H, there is some number 6, well, maybe different than 6, that you see at least one monochromatic copy, no matter how you red-blue color the edges. And now if you take this as the Ramsey number for H as the size of your window, and you move it all over the place in a much larger complete graph, again, in each of these windows, you find at least one copy, you average this through, and you get that you always see some positive fraction of the total number of copies you can even hope for. Because if your graph H has some number of vertices, K, you certainly cannot find more than n to the K copies. So again, this gives some positive fraction, but it sounds like this should not be, I mean, this is perhaps not optimal for, this is perhaps wasteful for every graph H, maybe apart from some trivialities. The theme or the question is, how much better can one do? So for this, let me count the number of copies in J simply as the number of homomorphisms from VH to VG. So, and then what's the monochromatic count in a red-blue coloring of a complete graph is just the number in the red graph, number of copies in the red graph plus the number of copies in the blue graph normalized by the total number of maps. So in rephrasing the Goodman's theorem in this language, it says that for every red-blue coloring, the monocount of triangles is at least 1/4. Which also, I mean, one way of realizing that modulo lower order terms, this 1/4 is best possible, is that you just take a random red-blue coloring. Well, then if the red-blue coloring of your complete graph was random, then roughly 1/8 of your copies are monochromatic in red, 1/8 of the copies are monochromatic in blue. So yeah, certainly one cannot hope to improve this 1/4 just using this simple observation. All right, so since this is a workshop on graph limits, actually let me reformulate this. Let me reformulate the Goodman's result once again. And at least to me, using the graph limits or graphons notation is actually much more convenient in for this topic, and it will be the theme for the whole talk, that one perhaps doesn't a priori need, or does not necessarily need the graphon language, but it will make the questions and also the result much easier to approach if one uses the notion of graphons. So anyways, so what does Goodman's, how one can rephrase Goodman's inequality, or this result of Goodman to the language of graphons? If you give me, so what would be like the analog of red-blue coloring of a complete graph? Well, you can always think that red is my graph and blue is just the complement. So, and instead of saying graph, I will take red as my graphon and blue as the complement of my graphon, which is simply 1 minus W. So it says that the T of the number of triangles in W plus the number of triangles in 1 minus W is at least 2 times the number of triangles in constant 1/2, which is the graphon analog of R' with density 1/2. So in particle, it's at least 1/4. And I will call a graph common. I will call a graph H common if it is like triangle in this sense. And what do I mean by that? For every graphon W, the H count in W plus the H count in 1 minus W is at least as the graphons were random 1/2. And of course, if the graphon was the constant 1/2, then the number of copies is just 2 to minus number of edges of H. Because for each of them, I need to get the correct heads on mine as the outcome of my coin. So what graphs are common apart from triangle? There was a conjecture in 60s that every complete graph is a common graph. And then in Dura and Rosta conjecture that maybe every graph H is actually common. So these are the 2 conjectures, and well, we now know that both of them are wrong. Actually, the conjecture of R dash starts being wrong as soon as K is at least 4. So apart from H, which would be which is common for trivial lessons and triangle, there is no other complete graph that is common.
Quick question. You are talking about graphs, finite graphs, and then you go to the graphons, whatever, and then you're talking about the densities. The density in a graphon isn't quite the same as density in finite graphs. There's an error about 1 over n. Right. But you are also talking about finite graphs, so I'm having a little trouble.
Yeah. So they're like the way how I define it in this talk, I defined what a common graph means only when we talk about graphons. So of course the notion predates graphons, and then the original definition was actually saying it's it will be a statement about a sequence of graphs. So this is really an equivalentary statement, and I perhaps wanted to save my time to state the original definition using graphs. But the small graph that plays game here, it will always be some fixed finite graph. But indeed, you are that was kind of what I was trying to hint, that using graphons makes stating and also working with this much easier, but a priori it's not needed. One can. So no clique is common apart from H and triangle, and also, so in particular, Burr and Rosta cannot hold, but around the same time as Thomason disproved the conjecture of R dash, Sidorenko found an easier argument why triangle with a pendant H is not a common graph. So, and then a few years later, it was actually shown that as long as your small graph H contains K4, that's a reason why H is not a common graph. So statistically speaking, almost no graph is common. A typical graph H does contain K4. So now sort of, after seeing this, it's now a question like, okay, so are there any other non-trivial graphs apart from a triangle that are common? Well, there are. Some of the examples of common graphs are cycles, or even wheels, which is a cycle with a universal vertex attached to all its vertices. Sidorenko graphs, I will come to this in a minute, what I mean by that. And as one more prominent example of a graph that is graph H that is known to be common is it's the 5-wheel. Okay. So maybe before I go any further, let me pause here and check if there are any questions.
Just a quick question. What is K sub K?
Oh, it's the complete graph on K vertices.
What was the reason for Erdős and Rosta to conjecture?
So, you know, it predates my birthday, so it's sort of hard for me to try to guess. No, I mean, I guess to be fair, like once you know, I mean, graph theory evolved since '60s, so
We're still early on.
So the way how we, like I said, it's hard for me to comment. But indeed, you are right that to some extent those conjectures cannot be more wrong than they are.
Yeah,
To some
part of my question.
So one reason might be the diagonal Ramsey number. So Thomason found like 4 to the t over t for the diagonal Ramsey number. I mean, the upper bound relies on Goodman's formula. So it was kind of natural to expect such a thing also holds for a general complete graph, which would then allow us to improve Thomason's bound. But that suggests that it's impossible.
Okay, thank you.
Oh. So okay. So I was saying Sidorenko graph. So actually, let me now move a little bit, say a little bit about what I mean by that. So a graph is called a graph H is called Sidorenko, and again, let me just state it using the notion of like the limit notion, define it only using graphons. But there would be also an analogous definition for sequence, where instead of W, I would consider some sequence of graphs Gn. So I call graph Sidorenko if graph H Sidorenko if its count in any graph on W is at least as large as if I replace W with a random graph with the appropriate density. In other words, like among all graphs, all graphons that have density P, the way how to minimize the H count is to take the constant function P. So a couple of observations. If your graph is Sidorenko, then it's common because to some extent, if you want to show that a graph is common, you need to lower bound the count in red and blue. And if your graph is Sidorenko, just by convexity, you have a good handle on both in red and both in blue. So you are in a good shape. Also, if some graph H should have a chance to be Sidorenko, it necessarily needs to be bipartite. As long as you give me a graph H that is non-bipartite, for example, I can take the complete bipartite graphon with any non-trivial density, like 1/2, for example. The H count there for chromatic reasons is 0 there, but so it certainly loses against the random graph. So, and as a remark, all known graphs H that are bipartite and proven to be common are also known to be Sidorenko. And a famous conjecture of Sidorenko is that whether let me use the pointer for the online people, whether this implication can actually be reversed. So what is known on Sidorenko's conjecture? Well, it has been proven for various classes of bipartite graphs, like trees, cycles, complete bipartite graphs, hypercubes, and more. And here I just listed set of people who are behind all of these results, and more on the results on this topic. But in general, it is still widely open conjecture, and the smallest open graph H where we don't know is if you take this Möbius ladder, or in other words, you take complete bipartite graph with parts of size 5 and you remove a Hamilton cycle. So that's about the Sidorenko's conjecture, but again, one doesn't need a priori graph limits, but having graph limits as a tool was very handy when one tried to look at sort of a weaker version of, or a relaxation of Sidorenko's conjecture, and the relaxation I have now in my mind is the local version of it. So in Sidorenko, we are trying to compare the H count. We are wondering whether the constant graphon is a global minimizer of H count among all graphons with a given density. So in the local version, well, we don't go through all the graphons W, but only we take the minimum over those that are close to the constant function P, and ask, is it the case that H is minimized in this ball by the constant function P? And the distance I have in mind is on graphons is the cut distance. So okay, so this perhaps sounds like the natural local variant of the conjecture. Well, in the actual definition of locally Sidorenko graph, there is some additional technical assumption on the L infinity node. That restricts a little bit further the graphons W we are minimizing over. Anyways, extending the result of Lovász, Fox and Way showed that a graph H, so it seems like that. Okay, it seems that there is a nice conjecture characterizing Sidorenko's graph, but it also seems that we are very far from understanding it. Well, in the local regime, we actually do have a full understanding. It was proven a few years ago that a graph H is locally Sidorenko exactly when the girth of H is even, and by girth I mean the length of the shortest cycle in H. Okay, so before I go any further, any questions?
I have a visual question. What is a K55?
It's a complete bipartite graph. I cannot count till 5. It's 5, 5, 5, which I also don't know what it is right now.
So other than the triangle, are there any non-bipartite graphs which are known to be common?
That's exactly on my next slide. Okay. Actually, on my next slide, I'm already skipping the circuit. Yeah. Okay. Anyways, that's a good question, and yeah, let me talk about it now. So, as you just recalled, triangle is known to be common, but not only a triangle, you can also glue triangles along edges or glue triangles along vertices, and again, you can show that, like, if you basically build up any tree that is consisting of triangles glued along edges or glued along vertices, it will also give you a common graph. Also, I think that on the previous slide, sorry, on the 2 slides back, I said that all even wheels are common. So an even cycle with a universal vertex attached to everybody. So that gives a class of many graphs that have chromatic number 3 and are also common. But for quite a while, and sort of kind of coming from the other extreme ones, Czech, and Thomason realized that containing a K4 is a good reason for H to not be common. Maybe already the chromatic number is a good reason to not be common. So in particular, they ask, is there any common graph with chromatic number higher than 3 that is common? And like the usual suspect, sort of the smallest non-3 chromatic graph H that is not containing K4 would be the 5-wheel. So I already spoiled it on my first slide to common graphs that 5-wheel is known to be common. And it was proven roughly 10 years ago by Hamed, Hatami, Honza, Hladky, Dan, Sergey Norin, and Razborov. And from nowadays point of view, it's a straightforward application of the Fleck algebra method. So in particular, it does rely on some computer assistance. And my understanding is that the Fleck algebra proof is the only way how we know that the graph is, that 5-wheel is common. So then the barrier of 3 was broken, but the following natural question would be, or at least to me would be, and it was to the group of the people, and the question was again reiterated by Conlon, Fox, and Sudakov in their survey on Ramsey numbers and Ramsey multiplicities. Is there a common graph with a given chromatic number K? So I guess that's what my title was of the talk was saying. So the main result is a positive answer, the positive answer to this question. So stating it is that for every K, there is a common graph HK that has chromatic number equal to K. And how does such a graph look like? Well, we actually have a slightly stronger result, and this chromatic bound is only a corollary of it. So more or less, our actual results says the following. You give me any graph F, and the only thing what I want from you is that the girth of your graph F is at least some small constant. I put here on the slide 42, but I guess it's not the best constant we have in the paper. Yeah, I like 42. So, and
now we know what it's the answer.
That's exactly was the logic behind me putting this last night on the slide. So you give me this graph F, I can decorate it a little bit. So I will attach some short path and a C4 on one side, and I will attach another path on the other side and place a complete bipartite graph at the end. And the statement is that just based on this graph F, there is some N0, and if the parameters M, N, and L play a little bit, some delicate game with respect to this F, this construction gives you a common graph. So I want to say something about the proof, but before I go any further, let me again pause here and ask if there are some questions.
Maybe you can tell us what the chromatic number of this construction is.
Oh, right. So why does this actual statement imply what I promised? Well, there is another well-known result of R dash that for any girth G and any chromatic number K, there is a graph that has girth G and chromatic number K. So now so in particular, I have candidate graphs F that have a large chromatic number and unbounded girth, so in particular girth larger than 42. And if I attach something to them, I will definitely not decrease their chromatic number. Can I comment on that only at the end? So I mean, it is sort of not important for what I want to say in the yeah. Let me go to that at the end of it. So what is the proof idea? We essentially split the proof we distinguish two cases in the proof. In the first case, we consider that this W, and if W, then also the complement 1 minus W are far from the constant graph on one. And if that's the case, then actually it's not, it's more or less a standard argument in extremal graph theory that either we can find in one of the colors, say in the red one, some subset of vertices which induces only a tiny number of edges, and in that case we would induct on S in blue and finish just by having enough copies of H in the blue color. Or if we don't find this sparse subset, then every vertex, yeah, I promised I will be pointing with this. Every vertex, essentially every vertex, or almost every vertex, lies in some positive number of copies H. Okay. And if and in this second case, the thing what we do is that okay, so on every vertex we have some positive fraction of copies of H, and also so far we haven't used that the graphons W and 1 minus W are far from the constant graphon, but now is the time to use it. So KMN is a Sidorenko graph. So in particular, both in red and in blue, we see at least as many copies of KMN as in the random, as we would see in the random one. But actually, one way of looking at it is that inspecting the proof why KMN is Sidorenko, why is it minimized at the constant function 1/2 or the constant function P, tells you that if you are far from this constant function, you actually get a positive boost. And that boost we're gonna exploit, and the parameters clash together correctly to conclude that indeed, in that case, we really see at least as many copies of graph H as we need. So the main part of the argument is actually lies in the other case. So namely when the graph on W is close to the constant 1/2. But then at least if I try to convince you in basically 1 or 2 minutes, well, the girth of this graph H is 4, and I told you that an even girth is a good reason for graph to be locally Sidorenko. So perhaps the first attempt would be to just finish by using Fox and Way result. Call it a day. So unfortunately, it doesn't. So we were not able to use this Fox and Way as a black box for 2 reasons. One of them was this additional L infinity assumption I mentioned in the definition of locally Sidorenko, but also, and a much more substantial reason was that for this interplay of the parameters of this construction, they sort of, I mean, this plan in the far case and in the close case sort of goes against each other. So we need, so in order to make this make these 2 options cover really all possibilities of graph on W, we need a stronger statement. We need a sort of statement where the locality bound would be independent on these parameters. But the control to have completely independent in the local Sidorenko, that would be too much to ask. But just in this specific family HK, yeah, we were able to do it, and then conclude that indeed that locally the H count is minimized by the random function. So, any questions? So to conclude, here's again the main result, which says that there are common graphs with unbounded with an arbitrary large chromatic number. So coming back again that like so a common graph is that you arbitrarily red-blue color. It's arbitrarily red-blue color the edges of a complete graph, or split your constant graphon 1 into 2 graphons W and 1 minus W. The Ramsey number, sorry, or I mean Ramsey's theorem, that's not something that it would be tailored to 2 colors. You can also L color the edges of the complete graph, and once it's large, once the complete graph is large enough, you see a monochromatic copy of your favorite graph H in at least one of the colors. So one can sort of play the very same game also in this multicolored regime. So again, let me just define what an L, what does it mean for H to be L common using the graphon language, using the graph limits language. So it says the following: no matter how you split the constant function 1 into collection of L graphons, L different for each of them, I think that they represent the graphon Wi represent the edges colored with color I. The monochromatic count is lower bounded as if those L graphons would be random functions 1 over L. So couple more observations on this L commonness. Once your graph H stop is not L common, there is a simple extension argument that says that it's also not L plus 1 common. So once it stops being L common, then it's never L prime common for L prime larger than L. And also, as soon as the chromatic number of H is at least 3, you can cook up some multicolor coloring of the complete graph where you beat the random coloring. So in other words, every non-bipartite graph stops being L common for some L0. But on the other hand, if H is Sidorenko, then sort of the convexity argument that I said for two colors again applies also here. I want a bound in the sum, and if H is Sidorenko, I have a control in every of the colors. So the sum is at least the average. So that's an implication. In one of the previous works with Fan and Dan, and also together with John Noel and Sergei Norin, we actually show that this is equivalent. And it's equivalent independently on Sidorenko's conjecture. So I mean, if Sidorenko's conjecture is true, every bipartite graph would be Sidorenko, then okay. Once the chromatic number is, once the H is non-bipartite, this cannot hold. And if you believe in Sidorenko's conjecture, then you have it for every bipartite. So if Sidorenko's conjecture is true, then this equivalence is actually trivial. But we show this equivalence even independently on Sidorenko's conjecture. And also in that paper, we provided the first example of a non-bipartite graph for L at least 3. So the particle triangle is not 3 common. There are some graphs that are not bipartite and are 3 common, 4 common, and so on. So, and this was sort of one of the starting points for our for the main result I was presenting today. And well, the natural question is whether one can generalize this, what I presented here, also to this multicolored setting. And long story short, yes, one can. Sort of conclude. Let me say a few more remarks and open problems in here. So I guess one of the smallest example for Sidorenko's conjecture is this K55 minus C10. So whether it's Sidorenko or not, that's sort of one of the current questions in regarding Sidorenko. But so if it is Sidorenko, then also it should be common. So maybe it's seemingly an easier problem would be to show that K55 minus C10 is a common graph. We don't know that. Also, few more comments on our construction of this common graph or L common graph with arbitrary high chromatic number. So there are a couple of features of this construction. For instance, so the graph is connected, but it's not too connected. So actually, at the end of our paper, we ask whether one can have a construction of a common graph, L common graph more generally, that has arbitrary high chromatic number and also arbitrary high connectivity. So it was shown by Ko and Junkyun Lee, who is in the audience, that indeed you can also boost the connectivity to an arbitrary and boost the connectivity arbitrary. So that's one feature of our construction that turns out to be not necessary. Another feature of this construction is that the girth, the length of the shortest cycle in all of our graphs is 4 because of the C4 here, but the C4 here is really just to make the argument more convenient. Yeah. The C4 here is really just to make some of our arguments smoother than without it, but there is lots of C4s also in this other side, and that's what we exploited, the boost in KMN. So an open problem would be an open problem is that can you also make the girth large? So to state it precisely, is there a common graph H that has high chromatic number, high girth, and high connectivity? I don't know. And I guess it's exactly 40 minutes now, so I should stop.
All right, thank you for this very nice talk. Are there any questions? We still have one. Yeah, maybe you want to get started on that?
Okay, sure. So this Fleck algebra method in one sentence, it's sort of like an automatized applications of, so lots of results in extremal graph theory you can prove using Cauchy-Schwarz. And using Cauchy-Schwarz, that's sort of linked to finding like sum of squares prove that some graph density inequality holds. So in one sentence that says everything, and on the other hand nothing, is that finding some certificate for some sum of squares certificate for an inequality that smells like semi-definite programming. And Fleck algebras is a particular translation of proving some graph density inequalities as find a sum of squares witnessing it. And since semi-definite programming can be solved using computers, I'm hiding some technical stuff under the rug, but you can use a computer to help you find your sum of squares.
Just wondered, how is it good? Because I tried to Google it.
Ah, sure. Fleck algebras, and it was developed by Sasha Razborov.
All right. Any further questions? Yes. I'll bring you the microphone.
Thank you. In the early part of the talk, just restricting to the case L equal to 2, you mentioned that K4 and K13 are the smallest non-common graphs. And there's also a result saying that any graph containing a K4 is not common. So do you expect, or maybe there's a counterexample saying any graph containing a K13 is not common?
Graph containing?
Any H containing a K13 is also not common.
I mean, once you not contain K13, then the degree is bounded, right? I mean, K1, like if you tell me that there is no K13, doesn't it mean that basically your maximum degree is 2?
Ah, I see. It severely restricts the class of graphs. I see. Thank you.
Thank you. Any final question? Not? Then let's thank Jan again for a wonderful talk.